Today is November 16, 2022. This is my 135th episode for C++ 17 2023 CUDA SQL OpenGL DBB Vulkan AR PND PNI AR for Advanced Recursion PND and PNI for parallel numerical derivatives and parallel numerical integration. Why parallel? Suppose we are going to compute curl of vector in 3D space with dimensions 100 by 100 by 100 points. In 3D, it amounts to 1 million points in 3D. This means 3 times 1 million plus or double. If we want better resolution, we can try 1000 by 1000 by 1000 points in 3D. It means 1 billion points in 3D space. That is 3 times 1 billion floating point operations at minimum. Huge. If we are going to handle such scale of points, we need to use parallel algorithms. So, parallel numerical derivatives, parallel numerical integration. As the title says, in this episode, I will discuss advanced recursion using Posterion and Fold Visitor. I implemented Posterion in this series of videos. Through C++ 17 2023 template metaprogramming, I created 187 videos to explain and implement PowerWorkers and Posterion. I'm very much disappointed in my Korean audience, so I blocked my videos in this channel. I opened only a few for my own use. I expressed several times, not just several times, many times, that I don't create my videos for commercial reason. Why do I share my source code and my video with those people who do not appreciate my own video, my own source code? I do not. I do not share my source code, my video. As I close this channel, I will close this channel too. This is my English channel. I will close all my videos in near future. I will share my source code only with people who have a membership. I will not share my source code with the general public. When I first began to film videos on C++ in 2017, I originally planned 3 years to catch up with the modern C++ programming. But then C++ 20 is released, then C++ 23. So it took me much longer than 3 years. I will completely close this channel by end of June next year. or year 2023. I'm proceeding on my own schedule. Actually, I'm a bit behind the schedule. After end of June next year, I will devote myself to mathematics and physics. I'm shutting down my channel according to my own schedule, not to my whim. I have to close old chapters to open new ones such as mathematics and physics, and I don't want to be disturbed through my YouTube channel. Open up Visual Studio, CPP 17 2023 parallel, new folder 135, Advanced Recursion. Click this button. 1. Simple.cpp. Select this folder. Click this button. 2. Better.cpp. Select this folder. Click this button. 3. Standard.cpp. Click this folder. Click this button. 4. Visitor.cpp. Ctrl V. We will close this file. Select one simple.cpp. Include CPG, SCD, extensions, namespace, CPT, CPG, types. We will create template, type name, P, concept, tuple, or array, underscore C, CPT, tuple, flat C, P, or CPT, SCD, array flat C. So we created a concept called tuple or array C. Now we create a function auto simple auto forwarding reference ARGs void test simple int main. Copy this function name, paste it here. Now we call this function AutoSum simple 1, 2. Now here return ARGs. We are using fold expression. Please understand that we are using single operator, so this is unary. We are using single operator. This is called pack. This is pack. This is fold. So with respect to pack, fold is on the right hand side. Unary, right fold. Now open up Microsoft compiler. dir cd 135 advanced recursion cl ehsc scd will be using C++20. 1 simple.cpp fe m.exe, hit enter. clsm, scd, cout, sum. I will be using cpg and we build again clsm. So the result is 3. Okay, now here we'll be using std tuple 3, 4, also std array 5, 6. Now the problem becomes much more complicated. These ARGs can be tuple or array. Of course, it does not build. No, it doesn't. How can we solve such problem? Now, here we create a lambda auto process ARG. We capture all, then auto ARG. It is lambda, so don't miss semicolon. Here, using ARG T, the type of this argument, deckel type ARG, then we will remove std, remove cb, reference T, like this. So ARGT represent ARG, the type of ARG. Now with this, we can call this function like this. Okay, we can call this function. This function should return value. Now, if context per, we can use this concept by passing argt. Okay, so if our argument is tuple or array, I will copy this, paste it here. If arg is, this arg is tuple or array. Otherwise, we can return arg. Okay, in this case, arg is neither tuple nor array. Now, here we understand arg is tuple. How can we call this function recursively? Well, we can try. Simple arg. Please understand, this does not work. Arg is tuple. So in this function is called with a new tuple. Then it is tuple, so it forms endless loop. Endless recursion. We can't do this. Instead, we can do return std apply. We pass simple, then arg. Now let's try it. It doesn't work, but let's try it. We rebuild CLS, we rebuild. It doesn't work. Okay, we cannot use std apply, does not work when simple is a function template. It does not work. So we failed. How can we overcome this problem? Well, we can make it lambda. So I make it lambda Okay, it is now lambda. Don't miss semicolon. Don't miss semicolon here. It is now lambda. So now it works. It works. Let's try. We rebuild. Wow, it worked. But this is not standard. This is not standard. Let's try with the GNU compiler 135 advanced recursion. I will try with the clang first. SED C++20 1 simple.cpp. Don't miss LTBB 12 or c.exe. Hit enter. It doesn't work. Okay, this part doesn't work. This is not standard. Luckily, we can use here this auto self. This is called deducing this, which is introduced to C++23. Okay, we introduce C++23 introduce deducing this. With this, we can use here self. Note that this is self. This self represents this lambda. So we can use this syntax. Now we have to use Microsoft compiler. It should be C++ latest. Hit enter. CLS-M. It works perfectly. But Clang compiler does not yet support deducing this, nor GNU compiler does not support deducing this. As of today, only Microsoft compiler support deducing this syntax. Once again, this does not work. When simple is a function template, it does not work. We have to make it lambda. Then we have to use deducing this auto self like this. This is simple, much simple to implement this. Now with this, we can try more advanced. For example, SED tuple. This tuple has SED array. Now 7, 8. In the tuple SED tuple now 9, then 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The result should be 55. Let's try it. CLS-M. So 55. These things are processed with this simple function. heavily recursive. We use std apply and self. Deducing this, it should be lambda. Now, let me explain how to analyze such program. Here, I create a block, then std, cout, arg, cpg, and there. I will set it 1, checkout, computation, order. Okay, with this, we rebuild CLSM. So, ARG is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The sum is 55. We passed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, we are visiting each element from left to right direction. Now, I will disable it. Let's check how this function takes arguments. Auto arguments std forward as a tuple args. It is parameter pack. We have to expand. Then std cout arguments cpg, and this is to check out how this function takes arguments. We rebuild CLSM. So initially, we take arguments 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 3, 4 is processed. Then 5, 6 is processed. Then 7, 8, 9, 10. 7, 8, 9, 10. Then 7, 8 processed. 9 processed. Of course, then 10 will be processed. Then 55. Also here, 3, check out the type of ARG. std cout type of ARG. We can say cpg get type name. This type ARGT. Then cpg, and there I will disable this part. Now we build again CLSM. So we can check tuple int, tuple int, then array int 2, then tuple array tuple, array tuple int, array tuple int, then array int 2. This is array int 2 is processed here. Tuple int is processed here. So the result is 55. Checkpoint 1, checkpoint 2, checkpoint 3. You have to have complete solid understanding. Also, in this video, I explained deducing this we are using deducing this. In this video, I explained how to use std apply. This function is very compact, but can handle such overwhelming data structure or arguments. In my next episode, I will give you more examples about advanced recursion. We need these techniques to implement parallel numerical derivatives and numerical integration.